So our approach, and my background is in the area of non-aqueous energy storage. So that means batteries based on lithium, sodium, non-aqueous based electrolytes. And we were interested in shifting the CO2 reaction out of the aqueous space and instead looking at ways to think about designing new reactions or new ways to control CO2's reactivity by changing the environment, the electrochemical environment around these reactions. And the goal was, or at least one goal, was to improve potentially the selectivity and our ability to control the CO2's reaction pathway by working in a medium that is aprotic, that doesn't contain water. We can restrict the various products that can be formed. Typically in our cells, we're forming things like lithium carbonate or alkali metal-based carbonates. And so that's advantageous for a couple of reasons. It allows us to potentially make a product with higher selectivity, and it also provides us a better platform to understand fundamentally how the CO2 is activated, how it reacts in these environments, and how we can learn to manipulate its conversion so that we can have high conversion efficiencies. Currently in the electrochemical field, researchers are looking at using metal catalysts, which serves to activate the CO2 for subsequent reactions. So we call that heterogeneous electrocatalysis. What it means is that the CO2 molecule, which is quite inert, can interact with the metal catalyst, and this metal catalyst can alter the electronic configuration of the CO2 and open up new pathways for the CO2 to undergo subsequent reaction steps by electron transfer and or ion transfer. And so this is sort of a classical approach, I would say. Cost is less of an issue, but what we understand is that converting CO2 to something highly reduced, like methane, requires up to 8 electrons transferred, so at least 8 elemental reaction steps. So it's a very complex pathway. And so there's no single material that is optimized for improving this reaction. We need to look at combinations of different materials, and it starts to be a very complex scenario. So our approach, rather than using the material, the electrode material, to activate the CO2, our approach was to use the liquid phase, the electrolyte phase, to activate the CO2. So typically in an electrochemical system, the electrolyte is considered to be a relatively innocent bystander. So it allows the reaction to happen, it allows ions to move around, but we usually don't think of designing the electrolyte into the reaction process. So what we have done with our most recent work is we've looked at using the chemical reaction of the CO2 with an amine, a concept that we took from the capture community, and we translated that into a non-aqueous electrochemical system. So now all of the activation that a material would normally do actually occurs spontaneously in the electrolyte. By the time we're doing the electrochemistry, the CO2 has already reacted into a more reactive form. And that allows us to avoid using metal catalysts.